Okay, so we can start with, we'll go down the list in order. So we'll start with implicit differentiation. Okay, so let me give you two examples that really drive home to me the point of implicit differentiation. If I say d dx, remember this is a verb. This says take the derivative with respect to x, and the with respect to part is really important. So if I say take the derivative with respect to x, is this a basic? Yeah, the variables match. This is just 2x. This is just our plain power rule that we know. On the other hand, if I say this, d dx of y squared, now I'm saying take the derivative with respect to x of y squared. Is this a basic? No, because this is not a plain x anymore. So that means that we need to have kind of an inside and an outside. So here's our inside, and here's our outside. So this is basically chain rule. So when I'm thinking of implicit differentiation right here, I'm thinking chain rule. So it says take the derivative of the outside, and you always leave the inside alone at that point, right? Whatever the inside is what it is. Times the derivative of the inside. What's the derivative of y with respect to x?
Y dx.
Yeah, dy dx or y prime, exactly, either one. So I often will do it this way when I'm doing it to begin with, just because that really is kind of driving home what I'm doing, keeping track of all the pieces. But here in a second we'll solve an equation. It's usually easier to write it this way with y primes because there's so many fewer letters. It's just a little bit easier to keep track of them. So let's look at a whole example. So find y prime if I'm going to try and avoid, I was getting ready to do a lin. I'm going to try to avoid having a lot of fractions for you guys to work through because that doesn't really help me know what calculus you know. That's a lot of algebraic manipulation. So I was going to put a ln x here or a ln y. The derivative of a ln is 1 over x. So as soon as I have a 1 over x, now I'm going to have fractions in my fraction, so there probably won't be a ln here for that reason. So let's just say okay, so I want to find the derivative. Can I solve this for y? If I could solve it for y, that would be a really good choice, because then I just take the regular old derivative. Is there any way to solve this for y? No, not with a y squared, and there's no way to do that. So that means we just need to take the derivative in place. So what are we doing? We're taking the derivative with respect to x. And go ahead and write that in. Remember, as soon as you start doing that, you don't write this anymore. This is your verb, but as soon as you start doing it, you take that instruction off. So this one, y squared, is that a basic with respect to x? No. So that's a chain rule, inside, outside. So we did this one already, 2y, and do dy dx for now. All right, so that's the first one. What about the second one? What do I see there? Product rule. If you're not sure, say it in your head. This is x squared times y. As soon as you say times, then you know you have a product rule. So if it helps you, go ahead and label first and second so that way you keep track of all your pieces. I find in this particular setup it's easy to do one piece of the product rule and not both. So just remember if you want to, just kind of start kind of grouping things, make sure you know where everything is. So product rule, first times derivative of the second. What's the derivative of y with respect to x? Yeah, y prime or dy dx. So this is the first part of the product rule. And then we have the second, which is y, times the derivative of the first, 2x. Okay, so we got that one done. Derivative of 3? 0. Derivative of 15?
0.
No, let's make it 15x. So I changed it to 15x. Okay, so now the next step that I usually do is I write a cleanup step just to kind of get everything back in order, and I replace all the dy dx's with y primes just to have less to write. So 2y, y prime. plus x squared y prime plus, and here, normally we write the number first and then the x's, then the y's. Go ahead and do that, 2xy. Drop the 0, 15. Okay, so given what we're trying to find, we're trying to find y prime. So the first thing we're going to do is throw everything that's not a y prime on the other side. This is very much like solving this equation. 2x plus 3x plus 7 equals 4. It's the same thing. How do I solve this? I collect up all my x's, and I put everything else on the other side. I'm going to do the same thing here. I'm going to collect up all my y primes, and put everything else on the other side. So when I collect up my y primes, I'm saying how many y primes do I have? You can think that's one way to think of it. I've got 2y of them here, plus x squared more of them there. Or you can think of factoring out the y prime. Either way gives you the same answer. So we'll have 2y plus x squared y prime. That's how many y primes I have. Everything else goes on the other side. And then what do I do? All right, just divide by this. All right, so y prime equals 15 minus 2xy all over 2y plus x squared. If I ask you to evaluate it at, remember sometimes we ask you to do that, that's when you would add that, the evaluation bar with, whatever the point is. That, I don't know. I have no idea that that's on the graph. So you would, if you had an evaluation, you would add that bar and go ahead and evaluate it. Which now reminds us very much of integration also, because we also have an evaluation bar when we do definite integration. Okay, so is this okay? Is this a good review of this? Yeah. So we also worked in here chain rule 2. And so while we're in this topic, I vote for doing related rates next because related rates is also chain rule. So let's just put all of our chain rule stuff together. Okay, so related rates. How do you know you have a related rates problem? It's a word problem, right? That's one of the things is that there are going to be multiple word problems on this test. So how do you know which one it is? So what are some tip-offs that you have related rates?
Like velocity or something?
Yeah, you're going to have something about rate. How fast is something happening? Because related rates, this is with respect to time. Okay? So these are going to be DDT. So you're going to look for the word fast, or rate, or what's another way to say something's changing? Change, rate of change. All of those suggest derivative with respect to time. Okay? So let's say an example. Let's do a ladder. So you've got a ladder leaning against a wall. This is not going to be very wordy, so I'm just going to kind of throw out some things. So it's a 5-foot ladder. I guess it's pretty short. 2 feet. The bottom is 2 feet from the wall. Sliding down the wall. At a rate of 1/4, let's do this, 3 inches per second. So the question is, how fast is the bottom moving? Everyone's got the picture? Ladder leaning against the wall, sliding down, so the bottom's coming down, the top's coming down, so the bottom's sliding out. Okay, so the question, how fast? As soon as I see how fast, and I also know that it's sliding down, and anytime I see per time, so many units per time, I know that I've got a rate there also. So anytime you see 2 rates in an equation, good chance that you're going to need to relate those rates. So the first thing you're going to do is draw a picture if you can. So let's look at the picture. So, well, first, find. Well, I guess we need a picture to be able to do that. And here's our ladder. We know that the ladder is how long? 5. You can only write a number on the picture if it does not change. Because this is a related rate, we want to know about the rates. So the only number that goes on the picture is the number that does not change. Does the length of the ladder change? Not in our present universe. So, so that's the only number that goes on here. Everything else gets a variable. So, we're going to do x and y. A and B, doesn't matter what you do, pick anything. Okay, so what are we trying, based on that picture, what are we trying to find? How fast is the bottom moving? So the bottom is x. How fast it's moving would be how fast? So it's a rate of change with respect to time. So that means it's a dx dt. So I'm trying to find dx dt. So remember, with related rates, the only thing that goes on the picture is any quantity that is fixed. Label everything else as variables. I'm trying to find dx dt. What do I know? I've got to know the other rate. Do I know the other rate? Sliding down the wall. Yes, I know this rate, dy dt. And what else do I know? 2 feet from the wall. So remember, the rates change. The rates, how they're related, change slightly depending on where the situation is. Exactly, that one fixed. So this is our fixed point in time that we're interested in. The ladder is moving the whole time, right? This is the one point in time we're asking about. So in this case, 2 feet from the wall, so x equals 2. We have a little bit of a problem here, though, don't we? Feet, inches. I wouldn't do this on a test, but just to remind you that your units have to match. So this one, instead of saying, this is 3 inches per second, but let's write that as 0.25 feet per second so that all of our units match. Again, I won't do that on the exam, but I just throw that out there. Okay, so you've got your picture, what you're trying to find, what you know. The next thing you need to do is find equations that relate everything. So the first thing you need to do, you're going to write 2 equations. The first equation is going to relate the quantities. You can't relate the rates until you know how the actual quantities are related. So the first one will be to relate just from the picture, no derivative yet. So how do these relate? Yeah. Pythagorean theorem. It is really important. I don't like to use A's and B's here, and I don't like to remember Pythagorean theorem with A's, B's, and C's, because that tends to mess people up if the letters get moved around. So just remember, side squared plus side squared is hypotenuse squared. Okay, and so now so this is relating the quantities. Now I need to relate the rates. That means I need to do a ddt of that whole thing. So is it a basic? Derivative with respect to time of x squared and y squared. Is that a basic? Any of those basics? Variables don't match, not basics, right? The only time you have a basic derivative is when it's a basic. It's just got an x, right? So here we have an inside and an outside on both of those. Okay, so the derivative, so chain rule, derivative of the outside would be 2x, derivative of the inside, dx dt. I like to keep it as dx dt rather than x prime. For implicit differentiation, I go to the primes just because there's a lot of algebraic manipulation. Here I don't. I leave them dx dt's to remind myself that they're rates related to time. So what's the next one?
2y times dy dt.
dy dt, absolutely. Derivative of 25? 0, always. Doesn't matter what variable you're doing that with respect to. Okay, so now I have related my rates. So now I need to go, I'm at a point where I can see if I have enough information. So do I have, and I'm trying to find, so I need to make sure I have all the other pieces. Do I have my x value? Yes. Do I have my y value? No. Do I have dy dt? Yes. So I'm trying to find this one. I've got I don't have this one. Can I find this one? Can you find a y value if you know an x value? Yeah, we come right back up here to this first equation. Okay, so I'm mixing up my classes. I think in my engineering class we ran into that. No, we did that here. There's another case we had in this class, right, where you use one equation to, maybe it's this one. Okay, so that's partly what this second equation is for. Oh, I know, for optimization problems, maximum. That's not on the list, but it could be. I mean, I didn't directly. So maximization problems are a possibility for the test as well. That's where we did that. So we'll do an example of those two. So plug in y here. So I've got an x, right? So here I've got 4 plus y squared equals 25. So y is going to be square root of 21. So I just plug that in. So you plug in everything and you get an answer. I don't know what it is because I've done this one before. So we'll end up with 2 times dx dt plus 2 times square root 21 times 0.25. I have no idea what the answer is.
Where did 4 come from?
2 squared. Because x is 2.
Oh, okay.
So I have no idea what the answer is. Is it positive or negative? Well, if I put this on the other side, that's going to be negative, right? So I expect this number is going to be a negative of some kind. Does that make sense to me? If my ladder is scooting out this way, what's happening to this? Except, we did it backwards. Did we do it backwards? Or did I just write it backwards?
Does it matter though?
It does. So let's come back. Yes, it does. So let's find the error. Sliding down the wall, because this is an important teaching moment. I'm sliding down the wall. So what do I know about dy dt? Is it getting bigger or smaller? Smaller. So if this one is negative, now when I put it on the other side, it will be positive, and that will be positive, and that makes sense, because if the ladder is sliding down the wall, then it's sliding out, and x should be getting bigger. So in my engineering classes, I call that the verify step. Make sure that your answer, interpret your answer, make sure it makes sense based on what you expect. So yeah, so this is an important thing. When we say sliding down the wall, when you are identifying this given bit of information, you need to pay attention to that sliding down. That means it's going to be, you know, if the quantity is decreasing, it's going to be negative. So that's important. Okay, so all of these are chain rule, along with the inverse chain rule we've done recently with integrals. So I actually kind of feel like chain rule is probably something that makes more sense now than it did before, because we've been kind of still using it. Any questions that anyone can ask on this? Okay, let's go ahead and do, while we're on word problems, shall we do a maximization? It didn't make our list, but I think that's because we all forgot about it, so let's do one. All right, so only because I'm thinking it up off the top of my head, so it'll be so much easier if I do a silly one. So let's say that you have, oh, we'll do an area. We'll do, all right, so so these are maximization. That's in. Which altogether would be optimization. I should have written. Okay. So, all right, so let's say that you have, fence is a good one. So fence, you want to fence an area along a river. You have $1,200 fencing costs. $3 per foot. What is the maximum area?
I thought you said optimization wasn't on the test.
No, I did not say that. Nice try. So, what do we think about this? It's the same process for related rates. We're going to draw a picture first, look at what we're trying to find, what we know, and try and put things together. We're going to have two equations again. one equation that we're working with and the other one that helps gives us extra information. So it's a kind of a parallel. That's why I wanted to do it right after. So the first thing we'll do is draw a picture. So what is our picture going to look like? We've got a river. And we're assuming that we're not fencing the riverside. So we've got our river flowing here. We want to fence, I didn't say rectangular, but we're going to assume rectangular area. So that's our picture. Let's label some things. Length and width, right? Because we tend to think about that with rectangles. Okay, so once you have a rough picture, now let's lay out what you're trying to find, what you know, and how they go together. So what are we trying to find?
Area.
Not just area, but maximum area. So when you start seeing this word, maximum or minimum or optimized, that tells you, again, that you're going to be doing a derivative. It's important to figure out which piece you're trying to maximize and keep that separate. So we're trying to find max area. And so what do we know? We know $1,200 cost. I mean, that's what we have, and we know $3 per foot. So we know that the cost is $1,200, and we know it's $3 per foot. So now we need to somehow relate some things. So we're going to have two equations, one for here and one for here. It's important you keep them straight because the maximized one is the one you're going to be doing the calculus on. That's the one you want to keep working with. Do not lose that one. So over here, we know that area is equal to length times width. And it might be a good idea to go ahead and write max in front of that, just to remind yourself that this is where your work is going to happen. Okay, this is where the calculus happens. So what's the other thing we know? We know that the cost is equal to $1,200. And how does that relate to the actual fence? How much fencing do you have?
3 times whatever L is, 3 times W, because it's per foot.
Right, so 3L plus 3W plus 3L again. So you can think of it, you can add up each piece like that, 3L plus 3W plus 3L. Or you could say it's 3 times however much fence you have, and the fence you have is 2L plus W. It's not the 2L plus 2W that you normally have because we're not going all the way around. Okay, so let's clean that up a little bit. So let's write 1,200 is equal to 6L plus 3W. It helps to clean up a little bit as you go. It helps to write things down. I really encourage you to write down extra steps. Sometimes people skip steps, and that's usually, they skip the writing down of the step, which often can lead to an extra mistake. Okay, so I want to maximize this. Looking at this, can I maximize it as it stands? Too many variables, right? So this is where I go back to that second equation to get more information. I can solve this for one of the variables, substitute back in. So I don't like writing L's, so I'm going to write 6L is 1,200 minus 3W. Ooh, so let's talk about this, 200 minus 1/2 W. How many of you like fractions? You all like fractions, right? So I could have solved this for W instead, and I would have no fractions. Does everyone see why that's the case? If I solve for W instead, now when I divide by 3, I get 400 minus 2L. Let's go with that. Will they both work? Yes. Will they both give you the same answer? Yes. So we'll just go with that. So that means that we have L times 400 minus 2L. So go ahead and multiply it out, 400L minus 2L squared. This is what I'm trying to maximize. Can I maximize that? And if so, what do I do? Take the derivative, right? Is this a basic? Yeah. The beautiful thing about this is once you get down to this point, it's really easy after this. So the hard work of these problems is sort of getting to this place. So now we'll do the derivative. 400 minus 4L. So if I go on a sign chart, L equals 100, right when I set that equal to 0. I know that it can't be less than 0, so I'm going to do that. And it will have an endpoint over here, but I'm not as worried about that. Can I assume that that's a max?
No, you have to.
You have to show me, because sometimes it's actually not. Okay, so in real life, And also, on a test last semester, because somebody was giving me grief about the sign chart, I put a problem on there for which, if you didn't do the sign chart, you got the wrong answer. So, it is possible. All right, so we put in, I don't know, 50 plus, here, minus, so yes, it's a max. If you like to draw on your sign charts, arrows, that's fine. When you get to concavity, if you want to draw, shapes, that's fine. That can help you kind of know where everything is. Okay, so it is a max. So we have a max at L equals 100. Have I answered the question? Yes.
And just to be clear, you get the zeros from the original function?
No, this is it. No. So this one, it said this equal to 0.
Okay.
Yes, sign chart always pertains to what it pertains to. And then that's an important thing. So, in fact, let's talk about this here. So I know that A prime, the derivative, equals 0 at L equals 100. So that means it's either positive or negative on either side. That's what the sign chart tells me. So this tells me it's going up, flattening ever so momentarily at the top, and then going back down. So at L equals 100, I have a max. What was my question?
What was the max?
What is the max area? Did I ask for dimensions? I did not. So this goes to your question though, where do I go back to get A? Do I go to A prime? No. So it's the same thing when you're talking about concavity and slopes and Y values. Always make sure to go back to the equation that gives you what you want. So here to get A, I need to come back here. I could come way back here, but then I'd have to get W first. So I might as well just use the one that's simplest. So A is 40,000 minus 2 times 10,000, so I get 20,000, I think. 20,000 watts. It's a word problem, so it needs a word answer. What would be my units on area?
Dollars per foot or something?
Area. Did I hear it? Square feet. And there's one way to know. Foot times foot would be square foot. So you can come up here. Your equations will often give you, and that's why with related rates I leave them dx dt, because it reminds me that my units are, I think we may have forgotten that on the last problem, my units are feet per second or dollars per year or whatever. It tells me what my units should be. Okay, so related rates and optimization problems work the same way in that. Picture if you can, write what you want to find and what you already know, and then write some equations that relate them. You're going to have 2 in each case. One that you're working with, and one that gives you extra information. Okay, so make sure to stay with the one you're working with and just only use that as extra, which is why I kind of set it up in 2 columns. However you want to organize it, that will help you. If you can stay organized in your writing, it'll help you stay organized in your solution too. Any questions on this one?